Okay, we'll take a look. Today, we are going to talk about probability. Just a couple things. So this week, you have quiz 2. That's going to be due on Sunday. And quiz 2, sometimes students ask, what is it? What do these quizzes cover? They basically cover just the content from the previous week. So it's not cumulative. You don't have to worry about chapters 1 through 3. It's going to just cover chapters 4 and 5. 4 we covered on Monday. 5 we're covering today. And I think everybody did the quiz. Maybe 1 or 2 students did not submit the quiz, and I'm not sure what happened. And then, but also, just make sure you keep track of your time. Okay, Gradescope will shut down, and basically, once you run out of time, you've run out of time, and they won't let you upload anything. So, make sure you give yourself enough time to scan and submit and upload your quiz. So, when you look at that timer, make sure you give yourself enough time for that. Okay. The scores for quiz 1, I believe, have been released, and so those are published, and please review that. If any of you scored, I would say less than 60, less than 60 on the quiz, please reach out to me or the TA as soon as possible, and come to office hours, and we'll try to get you back on track. Okay. The time to kind of address any type of concerns with the content or material is early on, not later. Okay, so while it's still fairly early in the quarter, I feel like we can start making corrections. But you wait around to the 5th week. The 5th week is only 3 weeks away, 2.5 weeks away. So don't wait around. Okay. We are here to help you. We want to see you succeed. Okay. All right. So anyway, let's get started and take a look at the material we're covering today. The big picture here for the entire course, again, is that we want to be able to make conclusions from data. We want to make conclusions about the population, even though we couldn't observe it directly. And there's kind of always this question that we have in the back of our mind, asking if we observe some kind of relationship or an association between variables in the data that we've collected and observed, does that mean there is a corresponding relationship or association in the population? Okay? Or could what we see in the data, could that have just been a random fluke? Could it just be a random fluke that is responsible for the patterns or whatever we saw? Okay, and so today we're going to learn about probability, and the reason why we have to learn about probability is because probability teaches us about randomness, and if we understand randomness, that will help us to decide if the data we saw was a random fluke, or if there's something more to it. Okay, so we have tools like the confidence interval and z-test and stuff, and that comes later. But today we're going to be learning probability to help us understand how randomness kind of behaves. All right, so chapters 1 through 4, which was kind of all of the previous week previous content that we've seen, that helps us to kind of describe data, describe relationships in our data. And today's chapter and chapters 6 and 7, we cover the basics of probability. All right, and again, we want to understand how randomness works. So here's kind of an example where this plays a role. Okay, so let's say there is a carnival game. In the carnival game, you spin a wheel. Half the spaces on the wheel are marked as lose, and the other half are marked to be win. Okay, so according to probability, we should win about half the time, right? If we've got 12 spaces and they're all the same size, and 6 of them are lose and 6 are win, we should have a 6 out of 12 or 1/2 probability of winning. Let's say your friend plays the game 10 times, comes back and says, I only won 3 times out of 10. I only won 3 times out of 10. I think the game is a scam. Okay? And what do you guys think, right? If the game is fair, we should win half the time, and if you play 10 times, you should win around 5 times out of 10. Okay? He only won 3 times out of 10, so that's less than 5 times. And because he only won 3 times out of 10, he feels like the game's a scam. So do you think this is evidence that the game's a scam? Or is it possible that our friend was just unlucky? Okay. And that's kind of the basic premise. This is the direction that we are headed in the future, is we want to be able to distinguish between, is something wrong with the game, or is something going on, or was the person just lucky or unlucky, however what perspective you have, right? That they only won 3 times out of 10. So we got to learn probability, and then we'll try to solve this type of question, in chapter 6. All right, so chapter 5 is kind of the basics of probability, and we'll learn about randomness and probability rules and all of this stuff here. Okay. So random. What does it mean to be random? So here, the definition we're going to use for random is that if an event is random, it means we cannot predict the next outcome, right? And in addition to that, there's no pattern in the outcomes. We can't predict it. We can't establish a pattern. Random is not the same thing as arbitrary. A lot of human decisions are arbitrary, but generally are not completely random. Humans are bad at identifying what's random and distinguishing and knowing something that's random. Okay? If you ask a person to create a random sequence of digits, right? Write down 20 digits in random order. It will often be kind of easy to tell whether a human thought of the numbers in their head, or if those numbers were generated randomly. Okay. And the more digits you ask, then it's actually easier to identify the human, because when humans do this, it doesn't look random. All right. But random doesn't mean that we can't draw understanding or learn to understand the phenomenon. So, for example, flipping a coin we generally consider that to be a random thing. Okay, I wrote it could be debated, but when you flip a coin, you can't predict how it's going to land. But we can say that in the long run, I'm looking for my coin. I guess I don't have one. But in the long run, we can understand that a coin should land heads 50% of the time. Okay, with a probability of 1/2, the coin should land heads in the long run. Okay. Now, there's kind of a question: is anything in life random? Because if you think about flipping a coin, if you knew exactly how much force, how much rotational energy it has, and kind of the air resistance and the bouncy, maybe we can figure out exactly how the coin should land. I think for our day-to-day life, we just consider a coin flip to be a random thing, but there's kind of a question of, is it actually random, or is it kind of the results of physics, and then is anything we do, I don't know, do we have choice over our words, or is it just the results of some physical process and stuff? Okay, but well, anyway, let's talk about probability. Probability establishes or expresses how likely or unlikely an outcome is going to be. And I want to just distinguish kind of between two notions of probability, the theoretic probability and the empirical probability. Today's lecture is going to focus mostly on theoretic probabilities, but let me talk about empirical probabilities too. Theoretic probabilities are long-run relative frequencies. Long run means the number of trials approaches infinity. And we can use mathematical rules to find theoretic probabilities. So, for example, when you talk about a coin and we say the probability the coin lands heads is 1/2, that is a theoretic probability. And we came up with that number 1/2 because we say the coin has two sides. Both of those sides have an equal chance of landing, and therefore the probability it lands on one of those sides, like heads, is going to be 1 out of 2, 1/2, 0.5. So that's a very simple example of a theoretic probability. On the other hand, an empirical probability is an estimate of a probability. Probability estimate based on kind of relative frequency of observations from experiments or a real-life process. And we use empirical probabilities to estimate probabilities when the math for a theoretic probability just doesn't exist. Okay? Now, this would be a silly thing to do, but let's say, I don't know. Let's say somebody has a coin and they did something to it. They altered it, right? They said, I bent the corner of this coin. I also, kind of changed the, soldered on some additional weight over on this edge of the coin, okay? And the friend says, I think this is going to change the probability with which the coin lands heads or something, okay? And now you really don't know, okay? So now this is something that looks like a coin, but maybe it's been altered. So you want to test this out. What's the probability this thing lands heads now? Okay, so we're not quite sure. We're not sure that the probability that a coin will land heads. So we test this out. We flip the coin 50 times. It lands heads 23 times out of 50. And so based on our experiment, our estimate of the probability that the coin lands heads is 23 divided by 50, around 46%. Now, is that significantly different from 50%? I don't know. We can't tell just by looking at this. We can do further tests. We can gather more and more data, or and so we can kind of try to figure that out. But that would be an empirical probability where you carry something out, you do an experiment to try to estimate its probability. Or on the other, another example is you go to the doctor, and there is a particular medical treatment that they're considering, and they want to say, what's the probability of success when you use this medical treatment? Okay. Well, there's no mathematical formula that you can kind of plug in to get this probability of success. So the way they give you a probability is they look at past records, and they say, you know what? If we look at other people who had the same disease, maybe similar background demographics, they're in the kind of the same age group, maybe the same gender, they're going to say, we had 100 of these incidents in the past, and of these, 100 cases, 80 of them had successful outcomes. Therefore, we estimate your probability to be around 80 out of 100. Okay, so they give you probability estimates based on past records, and that's an empirical probability. And in the kind of there's a connection in that theoretic probabilities are just kind of this idea of this long-run relative frequency. Empirical probabilities are based on relative frequencies, but basically from observations. And the idea is, if you were to look at empirical probabilities and you perform more and more and more of these real-life trials, so your observed frequency, as you do more of these things, your empirical probability will approach the theoretic probability. And that's known as the law of large numbers. And, the law of large numbers is basically how casinos stay in business, okay? So if you ever gamble, go to Las Vegas or something and gamble, all of the games are designed so that the theoretic probability of winning is a little bit in the casino's favor, okay? So if the game pays out even money, then the probability of winning will be slightly less than 50%, okay? And all of the games are kind of designed in this way so that in the long run, the casino will earn money. But they don't mind. Of course, anybody who goes to Vegas, there's a chance that they win money and the casino loses money, right? And the casino actually wants this to happen because that makes people willing to come back. Because if it was a guaranteed thing that every time you played money you would lose, then nobody would go to Las Vegas to play. Okay, nobody would gamble if it was guaranteed that you would lose every single time. So it's not guaranteed that you would lose. Sometimes players will win money and the casino will lose money, but the casino's okay with that because in the long run, with millions and millions and millions of players playing, in the long run, more people will lose money than people will win money, okay? And so that's how they earn their money. All right, so again, today we are going to focus on the rules for finding theoretic probabilities. Let me go ahead and give you your first view quiz answer for today. Week 2, Wednesday, your first view quiz answer is the letter B. B as in bear. B as in bear is your first view quiz answer. All right, so let's just say there's some event A. It could stand for whatever we want. And we talk about the probability of that event A. We say the probability of A is P of A or PR of A. And this just stands for the probability of A. And in the future, whenever I see this, I'm going to probably just read it as probability of A. And so if we say A is the event that the coin lands heads, we write the probability of A is equal to 0.5. Probability of A is equal to 0.5, okay? We can also write the probability of heads is equal to 1/2, right? What's important is we don't say A is equal to 0.5 because A is the event. The event itself is not 0.5. It is the probability of the event that's 0.5, okay? If we can't say heads is equal to 0.5. We say the probability that the coin lands heads is 0.5. The event is not the number here, okay? So you must say probability of A is equal to 0.5. Probabilities are always numbers between 0 and 1. That is to say, for any event x, 0 is less than or equal to probability of x, less than or equal to 1. The probabilities can be expressed as fractions or decimals or percentages, and I use these things interchangeably, okay? A lot of times, I might look at this and just say probability of A is 50%. Probability of A is 1/2. Probability of A is 0.5. And these are all equivalent. Okay? If the probability of an event x is 0, then that means x never happens. And on the other hand, if the probability is 1, then that means x is certain to happen, or that's what we have. Okay? We have the complement. The complement of an event is the outcome where that event does not happen. And we would write AC for A complement. We might also just write not A, okay? A lot of times I just like to use not A, but that's very kind of English-centric. So, kind of in other textbooks that are maybe a little bit more universal, you might just have a C, you might even have a prime, okay? If A is the outcome that a toss lands heads, then the complement of A is the outcome where the coin toss does not land heads, okay? Now technically, not landing heads includes all the outcomes where the coin doesn't land heads. So most likely the coin lands tails, but it also includes events like the coin rolls away, the coin lands on its side, the coin disintegrates midair or something. Now, we could simplify our life and just say if it's not heads, that means it landed tails. Okay, and we could say the complement of A is that it landed tails, and we're going to ignore anything else. But strictly speaking, the complement is just the outcome where that particular event didn't happen. And so if you have the probability of an event is probability of A, then the probability of the complement is 1 minus the probability of A. 1 minus the probability of A. Okay, in some simple cases, we have equally likely outcomes. And if that's the case, then, and you have some event A, A could be made up of several of these equally likely outcomes. And the probability in this case is just the number of outcomes that belong in A, and we divide by the number of all possible outcomes. So here, let's try an example. Let's imagine you've got this cup of M&M candies, and you counted up all of the candies. You got 168 pieces of candy total. 30 of them are brown, 25 are red, etc., etc., etc. And what you do is you shake up the cup, you randomly select one piece of this candy. And we ask, what's the probability that this piece of candy you selected is brown? Okay. Well, the answer is going to be, 30 of the pieces are brown, 168 pieces total in the cup. And if every single piece has an equal chance of being selected because you shook the cup, then we would say the probability of drawing a brown piece of candy is 30 divided by 168. So around 17%, 18%, 0.1786. 0.1786. I'm going to sit down. Okay, what about the complement? What's the probability that we end up selecting a piece of candy that's not brown? Well, you would just do 1 minus the probability of selecting a brown piece of candy. Okay, so probability of not brown is going to be 1 minus the probability of selecting a brown piece of candy. We do 1 minus the previous answer, 1 minus 30 over 168. If the previous answer was 0.1786, 1 minus that is 0.8214. All right, here is a table. This table shows us basically two different variables. One is what year of school is for a student, and also whether the student is from California or not from California. Okay, so let's pretend we have a total of 208 students in a class or something like that, and we have this two-way table, okay? And we have first year, second year, third year, fourth year, and then from California, not from California. And what we ask is we say, if I select one person at random from this table, what's the probability that the student is from California and is also a first-year student? And the answer, well, we have 40 people who count as being from California and being a first-year student. So our answer is going to be 40 divided by the total 208. Okay, so 40 people fit this description of being from California and being a first-year student, and we get 0.1923. So just under 20%, just over 19%, 0.1923, 40 over 208. Okay, what about, what if we ask this question, what is the probability that someone is from California or is a first-year student? Okay, in statistics, anytime we see the word or, A or B, that means A or B or both. It's an inclusive or, okay? in English and a lot of language, the word or is ambiguous. Is it an inclusive or? Is it an exclusive or? And so the same set of words can be answered with different words. Can be answered in different ways, right? So one question you can say, do you like chocolate or vanilla ice cream? Do you like chocolate or vanilla ice cream? And if you interpret that as an inclusive or, you'd say yes. Yes, I like those. Okay, or I like that. Yeah. Do you like chocolate or vanilla ice cream? Now, if we ask the same question another way, we could say, do you like chocolate or vanilla ice cream? Do you like chocolate or vanilla ice cream? Then you might answer, oh, I prefer chocolate, or I prefer vanilla, or something like that. Okay. Same set of words, but one is exclusive. We're expecting you to pick one versus the other. And the other one's inclusive. Is either one of these acceptable to you? Okay. And in statistics, it's always the inclusive. Is who qualifies as counting as being part of group A, part of group B, or possibly both. Okay. And so in this case, we would count all the people who fit into these categories. 40, 50. There's a total of 120 people from California. We've got the 40 first-year Californian, 55 second-year, 30 third-year, and 5 fourth-year students. Plus, is from California or a first-year students, so we also include these 30 first-year students who are not from California, and we get a total of 150 people. 150 out of 208, so something around 72%. 72%. We can think of this, the probability of A or B, there's another way to calculate that. Here's a Venn diagram, and we can say, okay, A or B is going to be the total shaded area. Now, if I do probability of A, that includes this entire circle, which includes both the blue and green part. Probability of B includes the entire yellow circle, okay, this circle, which includes the yellow and green part. Now, if I just do probability of A plus the probability of B, then I have double counted that overlap. I've double counted the center part. And so I would need to subtract off the overlap. I only want to count it once. I don't want to count it twice. So we can approach the same question. What's the probability that someone's a first-year student, is from California or is a first-year student? And the answer there is we could just take everybody who's from California, 120 people, and we can also add, everybody who's a first-year student. We've got 70 people who are first-year students. So 120 plus 70 is 190, okay? Now, that 70 is made up of 40 and 30. This 120 is made up of 40, 55, 20, and 5. And we can see if I just do 120 plus 70, I have double counted this group of 40 here. So when we do our calculations, we have to subtract off that count. So I would do 120 over 208 plus 70 over 208 minus the overlap, 40 over 208. And therefore, the total answer is 150 over 208, so around 72%. If two events are mutually exclusive, so this is another topic here. If two events are mutually exclusive, this means that these two events cannot happen together. The two events cannot happen together. So if A and B are mutually exclusive, then the probability of A and B is equal to 0. So basically, if A happens, B cannot happen. If B happens, A cannot happen. They cannot happen together. And therefore, if events A and B are mutually exclusive, the probability of A or B can be simplified. A or B, we can find this by doing probability of A plus the probability of B minus the overlap. And if you subtract off the overlap, then, but here there's no overlap to subtract, right? This quantity for the overlap is 0. So this just simplifies to the probability of A plus the probability of B. So if you know two things are mutually exclusive, that there's no overlap, you can just add them together. You don't have to subtract off any overlap. Okay. So an example of mutually exclusive events would be, what is the being a first-year student and being a second-year student? Those are mutually exclusive. Okay, a student cannot be simultaneously a first-year student and a second-year student. I mean, there's like weird things about like how many credits and you have this kind of standing or whatever, but it's either your first year or your second year or third year or something like that, right? So we say, what's the probability someone's a first year or second year student? We can just add the column total, 70 and 95. Don't have to worry about any overlap here. And we can just add those two together. We get a total of 165 out of 208. And that would be our answer there. When we're looking at these things, switching the order of A or B or A, that doesn't matter. Probability of A or B is equal to the probability of B or A. Same thing with the and. Probability of A and B is the same thing as probability of B and A. So when we're talking about and or, switching the order of these things doesn't make a difference. Okay, let's introduce this next topic of conditional probabilities. Here we have kind of some new symbols. We have this vertical bar here. This vertical bar stands for given. So this means we would read this as the probability of A given B. Probability of A given B. This is the probability that event A happens given the fact that event B happens. Okay, what's the probability that A happens given the fact that B happens? So here, a silly example that plays off of maybe stereotypes of Californians and Texans, okay? So the question is, who drives like a pickup truck, okay? So you've got the probability that someone drives a truck from California, given California, right? So probability of drives truck given from California. This is the probability that a person drives a pickup truck if we know, or if we're given the fact that the person is from California. Okay. Over here, probability of drives truck given from Texas. This is the probability that someone drives a truck if we're given the fact that the person is from Texas, okay? And so the stereotype is frequently that, in Texas, everybody drives pickup trucks, and in California kind of, we have a lot of people driving Teslas and Priuses, right? And so these are kind of, I don't know if they would be even rivals, but just, you can contrast one with the other. And we'd probably look at this and say, oh yeah, the probability of driving a truck if we know someone's from Texas is going to be higher than the probability this person drives a truck if we know they're from California, right? So just kind of, and of course, a lot of people in California still drive trucks, but perhaps there are more people in Texas who do. Okay, who knows, right? So how do we calculate a conditional probability? The conditional probability of A given B, the probability of A given B can be found by finding the probability of A and B, and we divide that by the probability of B. Okay, probability of A and B, and we divide that by the probability of B. And we can do this by finding the count. We can also, if you have a table, you can just take the count of A and B, and you divide by the count of B. One thing that's important, though, is you can't switch the order of these things. Okay, so when we talked about A and B, we can say probability of A and B is the same as probability of B and A. But if you do what's the probability of A given B, that's not going to be the same as the probability of B given A. Okay, what's the probability someone's from Texas, if we know they drive a truck, is different than what's the probability someone drives a truck if we know they are from Texas. Okay, so the probability of A given B is not the same as the probability of B given A. All right, so let's look at this. Let's look at this example again, and I've kind of written all of these answers out, but let's pay attention to kind of the phrasing and kind of the corresponding probability here. So I'm going to pick a person at random from this table. We got, again, this is just made up numbers. 2,745 people. I pick someone at random. Okay, this person could be from California driving a truck, from California not driving a truck, from Texas driving a truck, from Texas not driving a truck. Okay, we're going to say, what's the probability that a randomly selected person drives a truck given that they are from Texas? So if we know someone is from Texas, what's the probability they drive a truck? Here, we're basically going to limit ourselves just to this column of people from Texas. Okay, so we have 1,170 people. That's going to go in our denominator. Probability that someone is from Texas, that's in our denominator. In the numerator, we have people from Texas who drive trucks, 420. So this number is 420 divided by 1170. Probability that someone drives a truck given from Texas, 420 over 1170. We get something around 36%, 0.3590. Okay, what's the probability? Here I have, what's the probability that a randomly selected person from California drives a truck? So here, the piece of information that's given to us is that they're from California, and we want to know what's the probability they drive a truck. Okay, so now that we know that they're from California, that limits our denominator to 1,575. Okay, so when we select someone at random from the table, there's 2,745 people, but now we know they're from California. So we're going to say, what's the probability that a randomly selected person from California, we're basically just limiting ourselves to this California column. What is the probability they drive a truck? 470 over 1575, we get around 30%, 0.2984. 0.2984, okay? Now this is different, okay? The last one says, what's the probability a randomly selected person is from Texas? So that's the question that we want to know. What's the probability of Texas? And here it says, if we know they drive a truck, or given they drive a truck. So now we're looking at people who drive trucks. We have 890 people who drive trucks. Of those, 420 are from Texas. So we do 420 divided by 890. We get around 47%, 0.4719. Okay. If two events are independent, the outcome of one event is not associated with the outcome of the other event. Oh, here I kind of skipped over this. You can kind of go over this on your own time. Probability of truck in Texas, truck or Texas, Texas or California. These are some numbers you can kind of go over on your own. But now that we've introduced conditional probabilities, we can talk about independent events. When we have independent events, it means the outcome of one event is not associated with the outcome of the other event. If events A and B are independent, then that means the probability of A given B is the same as the probability of A given not B, which is just the same as the probability of A. What this means is to say that the probability of A is just the probability of A, okay? The probability of A given B, it doesn't matter. Whether B happens or doesn't happen, it has no influence on A. The probability of A happening is just the probability of A. It doesn't matter what happened to B, whether B, did better or worse, it doesn't matter, okay? It's the probability of A. So we'd say A is independent of B, okay? And if that's the case, then B is independent of A. And then the opposite is also true. A and B are not independent, so that if B is not independent of A, then A is not independent of B. Okay, so either these two events are independent of each other, or they're not independent of each other. All right, so before we get into any of the calculations, just conceptually, from the previous example where we saw some of these numbers, before we even have to look at the numbers, what do you say is driving a truck independent of being from Texas versus California? Is driving a truck independent of being from Texas or California? What do you guys think? So again, the concept of independence is the probability of A is not affected by B. So whether B is yes or no, the probability of A happening is the probability of A. So is the probability that someone drives a truck given Texas, is that the same thing? Is that the same number as the probability that someone drives a truck if they're not from Texas? Okay, and the answer is no. We're kind of playing off of the stereotype that in Texas more people drive trucks than in California, and so we're saying, so for it to be independent, we have to say driving a truck doesn't matter. The probability someone drives a truck has nothing to do with whether they're from Texas or California, okay? The probability that someone drives a truck is just the probability of someone driving a truck. But when we look at these numbers, well, we saw the probability that someone drives a truck, if they're from Texas, is around 36%. And in our case, what's the probability someone drives a truck if they're not from Texas? And, using our fake data, we got around 30%. So if someone's from Texas, there's a 36% chance that they drive a truck. And if they're not from Texas, or if they're from California, there's only a 30% chance that they drive a truck. So those two numbers are different. And therefore, we come to the conclusion that driving a truck is not independent of being from Texas, okay? Because these two numbers aren't the same. The probability of driving a truck, 36% versus probability of driving a truck given from Texas is 36% versus probability of driving a truck given not from Texas is only 30%. They're not the same. Therefore, this indicates that where somebody is from plays a role in kind of the probability that they drive a truck. So therefore, they are not independent. These two probabilities are not equal. Driving a truck is not independent of being from Texas. Okay. Does that make sense? And if driving a truck is not independent of being from Texas, then being from Texas is not independent of driving a truck. Okay. Now, it's a little bit funny to think of that because sometimes when you think of not independent of, you feel like one is caused by the other. But it's not that they're caused, it's just there's some kind of association between these variables. So if we know somebody drives a truck, then if that's the only piece of information we know about this person, we're going to say that person is slightly more likely, to be from Texas than if we didn't know if we knew they didn't drive a truck or something like that. Okay. Okay. Here's another example. And this one again, made up numbers, silly, is being left-handed independent of wearing glasses. And so in this case, we surveyed 200 people. Some of them are right-handed, 180 of them are right-handed, some are left-handed, 20 are left-handed. Some of these people wear glasses, some people don't wear glasses. Okay? And we ask, is being left-handed independent of wearing glasses? And if they are independent, then the probability of left-handed is just the probability of being left-handed. If being told whether someone wears glasses or not does not affect whether we believe they're going to be left-handed. Like, Does finding out, right? I say, okay, there's a mystery person standing behind that door, and you ask, what's the probability the mystery person wears glasses? Okay, and you'd say, okay, well, according to our data, 60 out of 200, 30% of people wear glasses. Okay, and I say, well, hang on, let me tell you something else about this person. This person is left-handed. Does that affect what you believe to, their probability of wearing glasses? And the answer is no, okay? And if we flipped it around, what's the probability somebody's left-handed? You could say, well, 10% of people are left-handed. Something like that, right? I'm just making up numbers according to our data. And I say, well, hang on. I want to give you another piece of information. Let's see if this affects your answer. This person wears glasses. Okay, does that affect your probability? And the answer there is no. So what's the probability that somebody is left-handed if we know they wear glasses? Okay, out of the 60 people who wear glasses, 6 are left-handed. So our answer is 6 out of 60. Probability that someone's left-handed given glasses is 10%. What's the probability someone's left-handed if they don't wear glasses? Okay, there's 140 people who don't wear glasses. Of those, 14 are left-handed. Therefore, the probability of being left-handed given no glasses is 10%. So these two numbers are both 10%. They are equal to each other. These two probabilities are equal. We'd say people who wear glasses and people who don't wear glasses have the same probability of being left-handed, and therefore wearing glasses and being left-handed are independent of each other. So you kind of check A given B versus A given not B. And if those probability of A given B is equal to probability of A given not B, that indicates to you that A and B are independent events. Okay, so if they're independent, the probability of A given B is equal to the probability of A given not B. If they're independent, you can kind of swap letters. In this case, the probability of B given A will also be equal to the probability of B given not A. So both of these statements will be true. Okay. But don't get these mixed up. Probability of A given B will not equal the probability of not A given B. And the probability of A given B will not equal the probability of B given A. Okay. Okay. So this was sorry, I didn't fix this slide from Zoom, but just think about this. Let's say two events are mutually exclusive. Event A and event B are mutually exclusive. So mutually exclusive means the probability of A and B is equal to 0. Now also, both of these events have non-zero probabilities. So the probability of A is not 0, probability of B is not 0, but the probability of A and B is equal to 0. So the question is, could these events A and B, could they be independent? Could they be independent? All right. So what do you think? Yes, the events are independent. No, the events are surely not going to be independent of each other. Or they might be independent, or they might not be independent. So think about this for a minute. Okay, what do you guys think? Who thinks A and B are surely going to be independent? Okay. What about A and B are surely not going to be independent? Anybody? All right, what about they might not be independent? Okay, all right. So like a total of 5 of you raised your hand, but that's fine. Okay, the answer is actually they are certainly not going to be independent. Okay, they are certainly not going to be independent. If you think about it, the mutually exclusive means the probabilities of A and B is equal to 0. Okay, so basically, if B happens, we know A cannot happen. And if A happens, we know B cannot happen, right? So the probability of A given B is going to be 0, right? If we know B has happened, what's the probability A is going to happen? Okay, the probability of A given B is going to equal 0. But the probability of A, if B doesn't, if we don't know whether B has happened or not, is just the probability of A. So the fact that the probability of A given B is going to be 0, and that's going to be different from the probability of A, means they're not going to be independent, right? Or another way to think of this is we can say B is influenced by the outcome of A. A might be influenced by the outcome of B, meaning that if B happens, we know A cannot happen, right? There's some kind of relationship, okay? And it's not necessarily one causes the other, but if we know that B has happened, we know A cannot have also have happened. So if A and B are mutually exclusive, they cannot at the same time be independent of each other. We're going through our material kind of quickly, and we'll end a little bit early today. Let me give you your second view quiz answer. Second view quiz answer is the letter A. A as in apple. A as in apple is the second view quiz answer today. Okay, if A and B are independent, the probability of A and B is going to be the probability of A times the probability of B. So the probability of A and B is going to be the probability of A times the probability of B. And we can extend this, and we can say if you have events A, B, C, and D, and if they're all independent of each other, then the probability of all of those things happening together, A and B and C and D, probability of all of them, is just the product of all of those things. The probability of A times the probability of B times the probability of C times the probability of D. Okay? And to however many you need. So let's say we have a special coin, and the probability of landing heads is 70%, and the probability of landing tails is only 30%. So this is some kind of coin where it's not equal chance of landing heads or tails. What we're going to do is we're going to flip the coin 2 times. And we're going to say coin flips are independent of each other. Here, what is the probability that the coin lands heads both times? Okay, so I've got the probability of landing heads, 70%. Probability of landing tails, 30%. And we're asking, what is the probability we get heads on both flips? Okay, so that we can think of this as heads on the first flip and heads on the second flip. What's the probability of getting heads on the first flip and heads on the second flip? Okay, well, coin flips are independent of each other. When you flip a coin, it has no influence on how the next coin flip is going to land, right? So we can treat these as independent, and we can say this is going to be, what's the probability I get heads on the first flip? And we're going to multiply that by what's the probability I get heads on the second. Well, the probability of getting heads on the first flip is 0.7, and then heads on the second flip is also 0.7. So these two things multiply to 49%, okay, 0.49. So we would get heads on the first multiplied by probability of getting heads on the second flip, 0.7 times 0.7, a total of 0.49. Okay. let's change this just a tiny bit. And we're going to ask, what is the probability that the outcome of the second flip, so we're going to flip the coin twice, so we still have this special coin that lands heads with probability 0.7. We're going to say we flipped a coin twice. What's the probability that the outcome of the second flip matches the outcome of the first flip? So it might be helpful in this case to write out what could possibly happen. When you flip a coin twice, you can get heads, heads. You can get heads on the first flip, tails on the second. Tails on the first, then heads on the second. You can also get tails on the first and tails on the second. So which ones count as the second flip matches the outcome of the first? Okay, heads, heads counts. Tails, tails count. Okay, this one, the second flip matches the outcome of the first flip. So now we want to know, what is the probability of heads, heads, of getting heads, heads, or getting tails, tails? These things, these outcomes are mutually exclusive. You can't get heads, heads, and at the same time get tails, tails. Okay? There's no overlap between these things. So because they're mutually exclusive, we can add them and don't have to worry about any subtractions. I can do the probability of heads, heads, plus the probability of getting tails, tails, and there's no overlap for me to worry about. Okay. What's the probability of heads, heads? Well, we did that earlier, and we said this is going to be the probability of heads times the probability of heads. This is 0.7 squared plus the probability of tails, tails is going to be the probability of tails times the probability of tails. That's going to be 0.3 times 0.3, or 0.3 squared. So our total probability is 0.49 plus 0.09 you get 0.58. So I got that written out here. Does that kind of make sense? Any questions? Okay, let's try this one. All right, well, you guys try it. If we flip the coin 4 times, what's the probability we get heads all 4 times? What's the answer there? Probability of getting heads all 4 flips. Okay, well, what's the calculation you would do? So maybe you don't have your calculator. Well, you would do what to what power? I think I heard somebody say it. All right, so this is the probability of heads, 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 heads. This is, we're flipping the coin 4 times. We need to get heads all 4 flips. Heads, 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 heads. So this is going to be the probability of heads times the probability of heads times the probability of heads, 4 in a row. So we're going to just raise this to the 4th power. 0.7 to the 4th power, I think. 0.2401. Yeah. Okay. So that's what we have. Probability of heads raised to the fourth power, 24%. 24%. Okay. What's the probability we get heads 0 times? What's the probability we get heads 0 times if I flip the coin 4 times? What has to happen for you to get 0 heads? 0 heads. Tails every time, right? You have to get tails every single time. So you have to get tails, 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 tails. So this is going to be probability of tails to the fourth power, 0.3 to the fourth power, 0.0081, 0.09 squared, 0.0081. Okay? Great. Only a couple more. This one's a little bit tricky. What is the probability that we get heads at least one time out of 4 flips? At least one head out of 4 flips. So we could think about what could happen. Possible outcomes. Okay, and there's a lot. Okay, with 4 flips, there's 16 possible sequences, but we could kind of categorize them, and we can say we can get 0 heads. That would be tails, 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 tails. Okay, we can get 1 head, and that would be heads, tails, tails, tails. We could also get tails, heads, tails, tails. We can get tails, tails, heads, tails, 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 heads. So you can get heads on the first and everything else is tails. Heads on the second and everything else is tails. Heads on the third, everything else is tails. Heads on the fourth, everything else is tails. Okay? And I don't feel like listing these all off. Okay? We can get 0 heads, 1 head. There's 2 heads. We can also get 3 heads, and we can get 4 heads. Okay. All of these, 1 head, 2 heads, 3 heads, 4 heads, okay, this would count as at least 1 each. All right. This one is the complement. So the probability of getting at least 1 head is 1 minus the probability of getting 0 heads. Okay? So 0 and at least 1 are complements. 0 of something, okay, 0 of something is the complement of at least 1. Okay? And this applies to everything in life. 0 is the complement of at least 1 occurrence. So anything you can think of, visiting Paris, it will happen at least once in your life or 0 times. Okay? Whatever you can think of, right? Winning the lottery, either it's going to happen 0 times or it's going to happen at least 1. Okay? Having a birthday, it's going to either happen 0 times or at least 1 time. Oh, that's kind of grim. What is the probability that we get heads at least 1 time? We're going to do 1 minus the probability of 0 heads. We found the probability of 0 heads. 0 heads was, we had to get tails all 4 times. Probability of tails, 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 tails. 1 minus this, so we're going to have 1 minus 0.0081, and this is 0.999919. Okay. And that's it. Okay. Oh, we're going to finish like an hour early today. Let me give you your last view quiz answer. Today's last view quiz answer is the letter C. C as in cat. There's a couple more examples in the textbook from chapter 5, and I've assigned a few homework prompts from chapter 5. But this chapter, relatively light and easy. And that's okay. We'll end a little bit early today. Have a great rest of your week, and we'll see you next week. Okay? All right. So we'll end a little early today, and we'll see you on Monday.